easy to attack it. Put the hood on, all the time me cashes. Aren't you like Bob Saget? Greedy, I can't pass it. Eating everything to get no fasting. I don't care what you knew me in the past tense. I ain't no Julian Styles, this ain't no last dance. Way past it.
If I stand, I can do this thing more than you. What are you doing? Like your business. Hey. You have disgraced me. I will disown you.
And you'll find some common threads throughout a lot of their work that they're doing. Sometimes what their field is, what they're actually studying, about that. One of those stories where what you see, what they're going to present on, feels a little disconnected from what they are studying. And both of them are in College of Sciences biotech program. And when they start talking about what they're doing, you'll think, that sounds more like bioinformatics. If you don't know what bioinformatics is, talk to me. I'm the bioinformatics professor, and I have lots of classes to sample. But nevertheless, in their own individual passions and looking at the opportunities that are available to them, we've actually created this interesting interface between the biotech and computational medicine side. And through the mentorship of their PI, of the researcher Kieran Vinajja, they have been able to really explore this work. And it's fascinating to me from a bioinformatics standpoint, but anybody in the biological side, you'll find it equally as interesting. So please welcome your Manuela.
Hi everyone, I guess you introduced already. So I'm Emanuela, and this is my colleague Ella Minton. We are research assistants in the Vinajja lab at USM. And this is our presentation on some of our research findings that we are currently looking at on the implication of PTEN regulation in breast cancer resistance. So we're going to go into a little bit of background about what cancer is, so that, like, I know most of the people here are not really into science, so I'm going to break it down. I'm going to break it down into simple terms for everybody to be able to articulate it perfectly well. So what is cancer in the first place? So we all know it's the abnormal growth of cells in the body, and then the spread, the aggressiveness of it. So in 2020, it was actually predicted and estimated that 9.96 million cancer deaths were recorded worldwide. But these researchers also found out that in 2040, there will be 30.2 million new cancer cases arising. So they came up with all these breakdown of estimates into the type of cancers that we have, and then the actual leading ones and the factors that lead to people getting these cancers, which would result from infection, alcohol consumption, and a whole lot of genetic mutations and factors as well. So as they were doing these research, breaking down into its estimates and then findings, they also came up. But they also saw that breast cancer was actually overtaking lung cancer, which became like the most diagnosed cancer as of now. So the clinicians and the researchers as well decided that, okay, why not break these types of breast cancers down into different types, and then so as to be able to know the type of, treatment to give to their patients. So they broke it down from the best prognosis you could get down to the worst prognosis that could come up. That started from the estrogen receptor negative type of breast cancer, moving down to the estrogen positive type of breast cancer, and then triple negative breast cancer, which is actually like the worst and the most aggressive one that anybody could get. So they also realized that, okay, why not we look at the types of treatments that we could give to patients, which could result from chemotherapy that everybody knows that when you get cancer you go through, radiation therapy is there as well. But the one that we are currently looking at is targeted therapy. Why targeted therapy? Because it inhibits, the mutated genes that drive the cancer. So these mutated genes, not all of the target therapies that these researchers use actually work. In a sense that there's something called adaptive resistance. So this adaptive resistance actually inhibits or it drives and then evolves the cancer that the person has, making the treatments that we are giving to the patient less resistant less effective. So they realized that 33% of women that have undergone the treatment of breast cancer development, they actually start developing adaptive resistance to this cancer. And then the question is why? So the why comes from the signaling pathway. So the cancer-driving signaling pathway allows the uncontrolled growth and then inhibits the cancer cell death. Instead of inhibiting the growth of the cancer, it ends up inhibiting the cell death instead, causing the cancer to grow and then adapt more to the treatment that we give to the patient. So they came up with, okay, why not we look at the signaling pathway that is contributing to the breast cancer growth. So we looked at the PI3 kinase AKT pathway, which is actually the most important breast cancer signaling breast cancer growth. So from here, they started with, okay, why not we treat these patients with inhibitors that will actually quench the cancer signaling, but they also saw that it was often leading to adaptations that allow the reactivation of the cancer signaling, leading to adaptive resistance, as I said earlier. So looking at this diagram here, paying attention to this section, this is where the adaptive resistance starts from. So this is the cancer cell and the tumor growing, and then the moment we start treating the patient with the drug, there's something called acquired mutation. So the patient starts or the cancer starts acquiring mutation, or there's something called adaptive resistance that I've been talking about. So the cells rearrange. Some of the cells die when you treat it with the drug, and then some of them start rearranging themselves and then start adapting to the drugs that we're using to treat the patients through all the treatment cycles. These cancer cells that do not die, that get adapted, end up regrowing in the human system. So they were like, okay, fine. They did the research, they found out that PI3 kinase inhibitors are actually help, stop the growth of the breast cancer. But later, even though FDA approved it for its use, later they realized that it doesn't really work well as a single agent. You will have to, add other inhibitors to pair well with other inhibitors to be able to stop the regrowth of cancer, which we are currently looking at. So I'll let my colleague here take you through the pathways for you to understand, and then we'll take it into the experimental details.
We do this by binding to the 3' untranslated region of the mRNA and facilitating translational repression. I'll hand over to Emanuela to talk about the experimental details.
Sorry to bore you guys. Okay, so we'll move on to the experimental details. So these are the cell lines that we are currently working with, and we are currently looking at BT474, SKBR3, MCF7, and then human fibroblasts as our controls. And as our that we are looking at, that we are planning on using to check the miRNA binding to the PTEN, include the target scan, human 8.0, PICTOR, and then microRNA target prediction database. So our future direction, what we are planning on doing to prove our hypothesis of mRNAs binding to the PTEN includes extracting the mRNAs, which we've done, and then we'll sequence it and then check if the mRNAs bind to the PTEN using the bioinformatics software databases to confirm PI/PK-driven mRNA binding to PTEN. Then afterwards, we are planning on knocking out the mRNA to confirm the spiral of PTEN decrease in PI/PK inhibition. Then lastly, our main focus is to design therapeutics to help overcome these adaptive resistance that we talked about through this whole presentation to PI/PK inhibitors in breast cancer. And then afterwards, we'll design an anti-mRNA and perform target prediction, and then rescue of the PTEN decrease on PI/PK inhibition. So this is our team. This is Radha. She's here. She's our collaborator and co-mentor. She's an associate research scientist from Memorial Sloan and Teaching Center. And our PI, who is also here, Kiran Banaja, he's an assistant research professor at the group here. And then our research postdoc fellows that we work with, Shabir and then Logan, they are also here too. So this is the end of our presentation.
All right, we're going to open it up to questions now.
Going through the experience. And more broadly, I think it's very important that we continue to bring back things that we learned in the industry into campus. The better we can do that, the better that we'll be preparing the students to come out and do different things and be successful when we get there. So I hope that both of you.
We have graduated! Finals!
Let's make you something for your birthday. Then. Here we go.
Hi! Hi! How are you? I'm good. How are you? To happy birthday. Ready? Go! To you! That was my day. Ready? Go! Happy birthday to you. Happy birthday to you. Happy birthday. Happy birthday to you. How old are you now? How old are you now? How old are you now?